Right. Assalamualaikum and good morning. So we'll continue with the lecture. Let me just get the file. Yeah. Right. In the last lecture, we have actually come to the point of introducing uh, relativistic corrections to replace, for example, can you see cursor? Yeah, okay. So to replace the kinetic term by the relativistic expression, and essentially that gives you an extra term here, and we treat this as a perturbing sort of term inside your Hamiltonian. So I think we have finished that. Okay, and come to the point of evaluating the what you call this first order energy shift. Okay, and one actually obtains this particular energy shift. So today we're going to look at a different one, which is coming from spin orbit interactions. Okay, so this applies particularly to the case of what we call an atom with one valence electron at the outer shell. Okay, so for example, the alkali atoms, and so essentially there will be some inner electrons come from the what you call inner shells, and the outer electron is called the valence electron. I believe you have come across this idea somewhere. Okay, so the thing is, due to the inner electrons in the closed shells, meaning closed with respect to filling up the shell completely, the potential that one has is no longer pure Coulombic in the sense of E squared over R, but will be some electrostatic potential phi R. Okay. So usually what happens in that particular case, the degeneracy that you get from pure Coulombic will no longer be there, and then essentially you can actually use the non-degenerate perturbation theory. Okay, so those are with respect to having this potential, but one should also consider the other thing. When you have all these completely filled shells, there will be spin inside. Okay, so there will be a spin orbit interaction. Okay, and essentially we want to discuss that. Okay? And this spin orbit interaction finally will bring us to the idea of a fine structure in your what you call energy spectra. Okay, so let's do this. So first of all, due to the inner shell electrons, also the nucleus, of course, the valence electron will experience an electric field. So electric field is given by the essentially the gradient of your potential. So it can be given as that. Vc is the one we have both. Okay. So you have the electric field coming from the charges within the inner shells, and then due to the motion of the electron of around the so-called the inner shells, okay, it will also produce a magnetic field, okay, from this particular in, no, your term involving your uh, electric charge sort of with velocity v, and then taking the cross product with the electric field that is caused by this inner electrons. Okay, and that gives rise to a spin orbit interaction. Okay, remember that this is coming from orbital angular momentum. So there, this magnetic field, which is felt by the valence electron, will interact with the spin of the valence electron. And the spin of the valence electron give rise to a magnetic moment, okay, from the previous formula that we have seen before earlier in the course, okay, given by that spin operator. Okay. So that would give rise to this interaction between spin. So this is coming from the magnetic moment due to spin, and the effective magnetic field that comes from the orbital part. Okay, so essentially this is the thing that gives the spin orbit interaction. Okay, so you just plug in all the things that we have previously, your b here, and then your mu here, and then essentially we have this slightly complicated thing, but you can reduce this to this operator. Okay, remember your E was actually given in terms of the gradient there, so you have to actually do the derivative, but you can the derivative was in terms of your gradient. Okay, so that will have a vector part, but suffice to convert this in terms of a derivative with respect to the radius, and then your vectorial nature goes into this. Okay, so this has, you have to go back to vector calculus. Okay, so you finally get this expression involving the derivative of the potential with respect to r, and then multiplied by L dot S. Now where is that coming from? This is essentially coming from your P here, that gives you your L. There should be another R cross P. Yeah, this one. So it's, I think if you put the sign right, that should give you that. Okay, I'm not sure. This is P cross R. Okay, so, oh, there's another minus sign here. Okay, that's fine. So in other words, you have R cross P, it gives you L, and you have your S over here. Okay. Now, this expression which we had sort of introduced through this potential phi here, and then calculating in terms of the electric and magnetic field. However, it's actually when compared to what is seen in experiments, it's actually larger than the correct one by a factor of 2. Okay, so this actually can be explained through a relativistic theory, which we hope we get to the end, introduce at the end of the course. Okay, so we will make correction with this by inserting a factor of half into this HI-house. So finally, what we want to do now was to look at this term as a perturbing potential to the, the original Hamiltonian, which is just given by your kinetic energy plus your potential early on. Okay, so let's do this. So we do a perturbation theory. Okay, and one of the things that we want to have is to have the eigenstate of this H naught. Okay, but you have to remember now your H naught involves well, in this particular case, it's just involving your orbital angular momentum. But the thing that we have to sort of consider is the perturbing part will involve your spin. So in other words, whatever eigenstates that we're going to have over here, we have to consider together with your spin states. Okay. So in other words, when you have spin states to be included inside this unperturbed Hamiltonian, there are two possibilities that you can actually have. Okay, so for the sets of unperturbed states, you can actually use either the individual angular momentum states, so involving your Lz and Sz, okay, or you can use your L squared and S squared together with your J squared and Jz. So this is from addition of angular momentum. But the point over here, we have to find out which is better in a way, because once you add your HLS, you have this operator coming in. Okay, so when this operator comes in, one of the things that we have already seen before, this will not commute with Lz and Sz. Okay, so the perturbing part, okay, will not commute with Lz and Sz, but it will, however, commute with the case of J squared and Jz. Okay, so in other words, there's a preference over here when you introduce this operator in the perturbing Hamiltonian. Okay, so in other words, we will use set number 2 to be used for your unperturbed states. Okay, so that's good. And the other, why we want to use that, one could actually use this first set anyway. No, I mean, it's just a theoretical nature of that, that it will not commute with that. Of course, the calculation will get more complicated. Okay, but the benefit of having this set to introduce is the fact that L dot S will commute with that. So in other words, it will already been diagonalized. Okay, these terms gets diagonalized under the second set. So in other words, once it's diagonalized, that means you have to remember your NLM are your original states. Okay, of course you can include your spin there, but over here you have to remember that these are degenerate for n greater than 1. So you know that degeneracy will actually make things a bit more complicated. Okay, but if you have the original eigenstate, the unperturbed eigenstates, already give you a diagonalized what you call matrix for your perturbing term, then you do not need to consider all this complicated version of the degenerate perturbation theory. That will only apply for the case of set 1. okay, which we will not do. Okay. Okay. So in other words, we're going to use this set to as a basis for your unperturbed states. So your unperturbed states are really your spinorial wave function. We have introduced this during when we introduced the spinors. Okay, so the spinorial wave function are simply just your wave function part put into a spinor form, where you have two what you call two components inside your spin part. Okay, the one over here will be just your wave function. The only thing that we have not really properly addressed, if you remember, we did this. This involved sort of fermionic spherical harmonics, which is not treated inside the book, but I did give you some reference to it. Okay, so you can actually see this is a bit more complicated than what's needed. Okay, but we will not use this. Okay, we will not use the fermionic spherical harmonics. Okay. In fact, we gave the spherical harmonics has come. The spin spherical harmonics comes from here. See, so you can see that this m is no longer integer. Okay? If it's integer, then you just have your ordinary spherical harmonics, but it's not. It's no longer an integer, and that will actually give you a different expression for the y over here. Okay, but never mind. We will not use this explicit form of what this is. Okay, but we will just use some algebraic result. So the eigenfunctions over here will now also obey the fact that it will be eigenfunctions of L dot S. Okay, remember that this commute with the states that we use. And your L dot S is actually given in terms of your J and your magnitude squared of your J and L and S in this way. Okay, you can refer back to the notes earlier. And for this, one can actually find, for example, your expectation value of that, okay, in this unperturbed states. Okay. So and this has been also covered earlier, so you might want to check back the earlier lectures. So when you do the expectation value over here, you will get two different results depending on the components of your spinorial wave function. Okay, for J equals to L plus a half, it will give you yeah, this one. Let me just check that back. Come on. Yeah, okay. You get for J equals to L plus a half equals to L h bar squared on 2. Okay. And for J equals to L minus a half, it will give you minus L plus 1 h bar squared on 2. Okay. So now this result will be inserted where it will be inserted in this we have to remember that your first order perturbation your first order energy shift, remember this is one something like that, and this is essentially given by your perturbing, so this is the perturbing potential. Okay. I have to rely back on the previous result of perturbation theory. So this perturbing potential, so this N naught, okay, the states, the unperturbed states, okay. So it will be just the expectation of your perturbing potential with respect to the unperturbed states, okay. So that's now will be inserted here. So in other words, this will come from where? This will come from your, let me see what notation I used. Okay. So this will come into your NLM HLS. Okay. So this gives you your first order energy shift. So include all those results that we have. So you get these two possibility of the values for the energy shift. The only thing that's left uncalculated is this part, okay, because that depends on what this potential is, which is going to be a bit more complicated to do, okay, because that's no longer your Coulomb potential, okay. But in any case, this shifting in terms of two different levels is called the Landis interval rule. Okay. Let's consider now, try to look at the case where you use an specific form for this potential over here, so that we can actually calculate this in full. Okay, so let's consider the case, or sorry, before we do that, here's an example of which you should be able to see the perturbing what I call it, results, the splitting of the energy levels. So before we go to the one that we calculate explicitly for this, okay. So let's consider the case of the sodium atom. The ground state configuration is given by this electron configuration. So you have your ground state electrons, the s electrons. There are two of them, and then you go to the next level, n equals to 2. You have your s shell fill up, and then your p shell fill up until the last electron will fill up the third energy level. Okay, so this gives you the valence electron. Now, one could actually say that this inner electrons, so there are 10 of them, 2, 2, and 6 give you 10. They form a spherical symmetry electron cloud, and then the third electron sort of orbiting this electron cloud. Okay, and this orbiting valence electron can also be excited from the s orbital to the p orbital. Okay, so when it does that, remember the energy levels are labeled by your numbers here. So this is your n. So really going from, say, s to p orbital, okay, from s orbital to p orbital, if you just follow this is called a principal quantum number. Okay, from the first cause. So if you just follow n, they are supposed to be degenerate, because your energy is just labeled by n. Okay, it's not labeled by your L. So But now what happens is that your inner electrons, okay, will give you a potential which is different from Coulombic. So even the S3s orbital and 3p orbital will also split due to this what you call inner uh, the potential caused by the inner electrons. Okay. Okay. I mean, we are not doing that specifically, but no, it's just an explanation of that. So there will be a splitting between 3s and 3p. But with respect to the say the p orbital, for example, it will also be split into no finer finer energy lines, finer spectral lines, due to the spin orbit what you call interaction terms. So let's see what it does. So your p orbital will be split into two, which is your p half and your p3 halves. Okay? And this is actually observed experimentally as what is known as a sodium D lines. So they will be splitting between, so this goes to the upper level here, okay, and this one goes one below, okay. And when it sort of excited from the S shell, okay, to the P shell, the P shell will have two different energy levels, okay, due to the spin orbit interaction. So when it decays back down, okay, it will emit photons, and when it emit photons, it will have two different wavelengths. Okay. Okay. So that is the part for the example where you actually confirm you have a spin orbit interaction. But in this particular case, your potential here is given by some unknown potential, which we have not specified. But in order to give you some idea what's involved, spelling mistake here, we will look specifically at the case of the Coulombic potential. Okay. But before that, just to give an idea of order of magnitude, okay, of what's involved in the splitting. So remember, we have the splitting given by this formula. We have that. Okay, and that sort of determines the splitting there. So we need to have a rough idea the kind of magnitude that it has. Okay, so over here one can see that if we look at what's involved over here, this is 1 over r, that is 1 over length. Your derivative is over 1 over length, and then your potential here has the dimension of energy. So it has the whole thing here has dimension of energy divided by L squared. Okay, and just from pure dimensional call dimensional consideration, okay, a combination from a combination of some factors, okay, which is you know that will be there inside your atomic kind of level kind of physics. It's going to be your charge and also your, this is essentially your Bohr radius. Okay, so from pure dimensional consideration, then this quantity can be obtained this dimension can be obtained from this particular combination. Okay. Maybe I'll let you do this as an exercise. Okay. Remember, there's a bit of complication over here because you have your charge squared. Normally we don't consider the charge dimension. Over here you need to do that because your charge is involved inside your what you call energy term. Okay, but if you have problem how to do this, just let me know. Okay, but you do have to convert this in terms of your E squared goes in terms of your E. Okay, so in the end what we'll have is that your fine structure splitting coming from the spin orbit interaction will be of this particular form. Okay, and normally one needs to compare this with other kind of splitting so that you'll be able to recognize this which splitting comes from where. The other kind of splitting is from say from the simply the ordinary Balmer line splitting coming from say your different ends end level, and this is essentially of order E squared over here. Okay. So making comparison between different sort of scales, you can see over here there is this E squared on MEC. Okay, you make comparison with other things, okay, which is coming from Compton wavelength and the Bohr radius. So you make comparison between the scales. The scale is in terms of this ratio here. So your Bohr radius is essentially 137 square greater than this this quantity. Okay, so you can see how small this is. Okay, where is this coming from? This 137, it comes from that quantity, which is I mean there should be an H bar and C here. Okay, I'm not showing you in the full notation, but no, these are actually given in the more advanced. Well, I mean this is already advanced. If you see the text for advanced quantum mechanics, this is known as the fine structure constant. I think I've mentioned that somewhere. Yeah. So that fine structure constant sort of determines the fine structure splitting, and you can see that that is quite small compared to say the Bohr radius. Okay. So now so that's settled in terms of magnitude. Now is the part where I mentioned before that we want to do explicit calculation of the derivative of this potential. So in order for us to do that, we would not want to consider the electrostatic due to the electrostatic potential due to the inner electrons. We will just have a one electron ion. Okay. So in other words, we have the nucleus and simply just an electron orbiting around it. Okay. And that is going to be given by just your pure Coulombic potential. And that you can actually do. So now remember that this is supposed to of charge ZE, the positive charge. So your potential will be something like minus ZE squared on R. Okay. So taking the derivative of that, so you know that you get 1 over R squared, and 1 over R squared multiplying this 1 over R gives you the 1 over R cubed. So in the end, to determine the spin orbit splitting, the fine structure splitting, we need to find out the expectation value of this quantity. Okay. So again, even this is not it's not readily available. You need to do some tricks. Okay. So how do we do this? So recall if you have some observable or some operator which is compatible with the unperturbed Hamiltonian. So what does that mean? That means I have some observable which is having this commutator to be equal to 0. Okay, and that will immediately tells us, okay, the matrix element is going to be just 0. Okay, but what happens over here is you really want to have the what you call the matrix element of this A over here. Okay, so let's look at a possibility of uh, uh, what you call an observable A which is almost commutes, okay, almost commutes with your H naught. So this is given by your radial momenta. Okay. Remember your momenta is remember it's supposed to be H naught equals to P squared on 2m plus V there. This part you can use your, remember this is supposed to be your suppose your P is simply given by minus IH bar del. Okay, and what one can do, your del is simply your ddx, ddy, ddz, but now you can convert this to spherical coordinates. Okay, what happens in that particular case, plugging your spherical coordinates into that, then you get your called kinetic energy due to the radial momentum, and then the other part will turn into some angular momentum contribution. So this was treated when we solved the hydrogen atom in the first course. So I don't know how much I can't remember exactly the whole thing is, but your H naught is something like PR squared on 2m, and then you have what we call the centrifugal barrier, and then your Coulombic potential. Okay, so in the end, okay, your PR of course will commute with that. Okay, your PR will commute with that. So the only thing, it doesn't quite commute with these two terms. Okay, but you know that these two terms are spherically symmetric. Okay, so you go back to the first course, and for spherical symmetric potential, okay, this is actually true. Okay, so in other words, despite that your PR doesn't commute with your terms over here, but we know that due to the spherical symmetric potential, your L commutes with H, and that will also say that your PR will also commute with H or H naught. Okay, so you still have this part to be equal to 0. Okay. All right. So we can use that now to actually get the expression we need for your spin orbit splitting, which is which is this one here. Okay, and let me see what. Yeah, it's actually here. So we want to calculate that. Okay, so we have to find how will that actually arise from this commutator. Well, you can replace your PR by the operator version, which is minus I bar DDR. Okay, and essentially calculate the commutator using this operator explicitly. And when you do that, you have to take the derivative of R for this term and then this term, and that will give you the things that we need. Okay. So over here, we also need to use some earlier results. So this expectation value of this together with expectation value of this will actually add up to give you a 0. Okay. So this one we have actually calculated earlier from, remember that this part is the one that really one needs to address is this R squared here. We have calculated this form. Okay, I can't remember which lecture, but this has been calculated as that. Okay, and what is En naught over here is your essentially your hydrogen atom sort of energy levels. Okay, so we have already calculated this, so we can actually now calculate that thing. Okay. So once you calculate that, okay, trying to get the logic here. Once you calculated that, and because these two things add to 0, the expectation value of these two things will add to 0. Since I know what that is from this one, I should be able to get this. And this one is the thing that we need because this is over R cubed. Okay. And the quantity that we want to calculate here is actually the 1 over R cubed. Okay. So putting all those together, I have not done the calculation in full here, but you can put all this together and then you'll find that your final expression for that derivative of the potential here is given by that. You can see that this comes from there, and this one will come from your this one here. Okay, so for the full calculations, I suppose one can give you as an exercise for you to do later on. Okay, so finally one obtains the whole thing, okay, combining with the earlier results that we had. Okay, we already had this thing. Okay, the only thing that we didn't calculate just now was actually this derivative of the potential. So we have done it for the case of the Coulombic potential, and we finally get the answer. The first order energy shift will be given by that. Okay. Now people has actually done this calculation for in terms of a much more relativistic form. Okay. For the relativistic form, one needs to use the Dirac equation. And one of the things that we see over here is perhaps needs to be highlighted. Okay, is the fact that you have L over here, you have L over here. These two L cancel for this part of the numerical answer here. Okay. And when this cancel, you actually observe a non-zero shift for L equals 0. Okay, so this was not really there before. So here we do have that non-zero shift for the S shell. Okay, so that was the new thing that we get from the spin orbit coupling. In this context, is for the case of the Coulombic potential. Now, okay, this is also in the case of the relativistic version. This is actually attributed to this so-called Darwin term, but we will not cover this. Maybe if we do this, probably in the where we introduce the direct equation. Okay, that is as far as how much my notes are there. So the next thing that one needs to do is I have to use the book instead because I have not prepared the notes. So let me just see where we are supposed to be. So this is about okay, 330. 340. So the next thing that we should be discussing is essentially the Zeeman effect. Okay. So again, I've not prepared for this part of the lectures for the notes. I'm still typing it. So there one would actually need to use what you call one has to express your magnetic field terms in terms of your vector potential. Okay, and this can be done in this particular form. Your potential is given by your magnetic field here, and using the gauge potential really requires you to choose a particular gauge. Okay? You need to choose a gauge. And the gauge being chosen here is essentially your symmetric gauge. Okay, and we have to apply this to your Hamiltonian. Okay, so here remember this is your like your previous H naught here, and this will be the new term coming in through your gauge potential. So I think probably since I do not have a good preparation for this, probably we can treat this for the next lecture in the Thursday lecture. So we'll finish early today, if that's all right. Okay. So I will stop there today. Okay. Sorry about that. So I have not completely finished out the notes. Let me get the attendance. Where is the attendance?
Know when's the due of for our quantum
Sign.
mechanics SCL?
Oh, the SCL. The SCL. Uh, when do you think? What week is this? I've completely lost what week is supposed to be.
Week 12,
Week 12. Next week.
Monday, or anytime next week.
Anytime next week. Okay.
By the end of next week.
Okay. By the way, we still have to. You have to hand in your assignment, right? So you have to tell me which day is best for you.
We agreed upon Wednesday for assignment, right? This Wednesday.
Because I don't think we did any decision on that. So
Uh,
Wednesday, since you mentioned it.
I'm okay with Wednesday.
Can we do it? Can we push it a bit, tiny bit further?
Wednesday plus epsilon. Thursday.
I'm okay. It's
Are you
just
okay?
tentative.
You can hand it on Friday. It will just delay the solutions. Okay.
I'm worried
That's
about.
the thing.
I think Thursday is okay, right? And also,
Um, okay.
Okay.
Although I have a test
Let's
that
make
day.
it Thursday, so that solutions can be out by Friday. Okay.
Great, doctor.
All
all
right.
right. Thank you.
Okay. So stop now. Okay. Thank you, everyone.